Okay,
Cool.
our next speaker, Daniel Gaines from JPL.
Thank you very much. So I'll be presenting today some ongoing work that we're doing at JPL to increase productivity for future surface rover missions. And the impetus for this work comes about, so we do actually, our rover missions I think are very successful. Speaking as one of the people who operates them, I like to believe so. But they do have a challenge, and that is that maintaining high levels of productivity can be quite challenging. In particular, it takes a great deal of human effort to develop the command products that we use to operate the vehicles, and it often takes more days, or what we call sols, on Mars to accomplish the objectives we want to get accomplished. And so the Mars Technology Program has asked us to conduct this study to try to identify ways that we can change how we design and operate rovers such that we can increase their productivity. And we just finished the first year, this past FY16, and now we're on to the second, this is a 3-year project. And one of the major accomplishments for our first year was we conducted a very intense case study of MSL operations to make sure that we could understand what the real productivity challenges that we're facing are, so we can make sure that the designs we're coming up with are addressing those challenges. So in this talk today, I'll present a little bit of overview on that case study. It's a very detailed case study. I'm not going to have time to go into all the findings, but I do have a report online available for everyone, and which I'll point to at the end. If you want to get more information, you can look that up. I do have a couple slides talking about background on the mission. I'm going to actually leverage some work. The context Eddie gave on his 2020 talk yesterday will be helpful, so thanks for that. A couple points. So this is actually an example of a sol from one of our actual sols for the Curiosity rover. And a couple things I want to note is the green boxes represent communication passes. Those are very important parts of the rover's day. The first one in the day is the uplink, and so we define that's sort of the start of the rover's day. And Eddie talked about handing over to the next day's plan. This is where those next day plans come from. They get uplinked our command products, and we hand over to that from the previous control sequence. And then there's other communication passes that happen during the day. Those are downlinks where we relay data across our relay orbiters down to Earth, and that's how we find out how things went, what data was collected, what it was up to, and then based on that data we can come up with new plans. I put a star by one of them, and that's because that's what we refer to as a decisional pass. And what that means is the various passes, depending on the alignment of Mars days to Earth days, those are going to come down at different times of the day. We're going to start planning, say, at 8 a.m. today, for example. Whatever pass happen to get data down in time for it to be before that day's planning session begins, that's all the data we're going to be able to use to make decisions in on that day's plan. And so the last pass that gets us data to inform that next day's plan is called the decisional pass. And the rover can still do things after that pass. It can collect data, but we can't respond to that data while we're coming up with that plan. So we won't know what it has done, perhaps if it got into trouble, we won't know about that till the following day, and we can't respond to it in the current day's plan. So that's one thing that's important. The other thing that's important is when we organize activity in terms of these blocks of activity. So here we have, before we're going to drive today, and so we do some pre-drive imaging, then we have a block that represents the driving, and we have a block after that to do post-drive imaging. And the reason we organize things into blocks, part of the reason is that we can control to make sure if there's uncertainty on Mars, and if things don't run as we expect, maybe they run too long, we can make sure that an earlier block, if it's running long, gets stopped, gets cleaned up before we transition to the next phase of the day's operations. So for example, while it's important to do the pre-drive imaging, we decided we don't want to risk losing the drive, and so if the pre-drive imaging runs long, let's cut it off, clean it up, and move on with the drive. Within each block, this is something Eddie also talked about, so we have a set of activities inside these blocks, but again, as I mentioned, we don't have great certainty on how long things will take. There's uncertainty about exposure times, autofocus times, compression times, and things just slewing times, so things may take longer or shorter than we expect, and so we build in margin, some slack time, because we don't want to we'd like to avoid cutting things off if we can, because it's important science. So we have margin time we build in, and if that's even not enough, we have cleanup time where we want to make sure the instruments aren't left in some unknown, uncertain state. We get them back to a known state before we move on with, for example, driving. Okay, one more piece of background is this notion of restricted sols, which is similar to the decisional information we talked about before, but on a multi-sol basis. So again, Mars days and Earth days have alignments, depending on what time it is on Mars relative to Earth, and I've showed daytime versus nighttime, and they drift over time. Mars days are about 24 minutes longer, about 40 minutes longer than Earth days. So over time, this alignment shifts. And so when we get into certain patterns where the end of day data from the rover comes down late in the day on Earth, and at the start of the mission, we would actually show up at work at that time and work overnight, but we don't like to do that because it's very stressful. So that was only for the first 3 months. For the rest of the mission, we go home, we go to sleep, the data just sits there. We wake up the next morning, come up with a plan, and send it to the vehicle for this day. And that works fine, except for the fact that this middle day here, the rover didn't have anything new to do. So what we do is we give it 2 days worth of operations. So we give it 2 sets of command products, one for this sol and one for this sol, and also covering the night as well, to get it over to this next handover period. But the problem with that is, as I mentioned, we only can, when we're working on this plan, we can only use the data we have on the ground so far to make decisions. So we're not going to know what it did during this day. And if it changed its state dramatically, like it drove somewhere else, we wouldn't know what environment it's in, what it's seeing. So if these cool science targets we identified in its post-drive imaging on this day, if it drove this day, we can't do anything about it because it's not near them anymore to collect data on them. So what we do is we restrict what it's allowed to do, which is why it's called restricted sols, such that the state that it's in pretty much remains consistent with what we knew about its state from this data. And that way we're more effective in controlling it. Okay, so moving on to our case study. So the objective of the case study was try to understand what is making it challenging to be highly productive for extended periods of duration. And so we designed an exploratory case study to answer these questions, basically what factors promote and inhibit productivity. And we also wanted to find out what is being done with these ground and loop interactions. How are the scientists and engineers identifying what activities they want to put into the plans, and what are they doing with these ground and loop decision points? So the case study was designed using structured interviews with operations personnel, both science and engineering, as well as detailed case studies of individual campaigns where we looked in detail everything that was done with the vehicle during those days, why it was done, and how it came about, and what the decision flow was like. And I'm not going to have time to go into, as I mentioned, in great detail into this, but I'll give you some highlights and refer to you or report at the end of the talk. This is an example of the case studies we chose. We wanted to get a sampling of case studies to give us a variety of objectives in different contexts, but also some similarity in objectives. So for example, this Pahrump Hills campaign in Marias Pass had a common objective of exploring a geographical region, whereas this campaign, we call it the Artist Drive campaign, was the objective of getting to a distant target location, a long-range strategic drive objective. We did set the scope of our case studies to bound the time. It's very manually intensive to do this case study analysis. So we focused on sols and campaigns that focused on remote sensing and driving. So we didn't focus so much on sampling and remote sensing for the campaign studies. So a couple takeaways. We did a variety of analysis to identify how productive these campaigns were and what was limiting and promoting productivity. And the first thing we did was look at sol by sol, how much of that sol was contributing towards campaign objectives. And so these pie charts are labeling sols based on how well or how unwell, I don't want to say poorly, but how unproductively they were contributing towards the campaign objectives. So the blue and the red you can basically think of as those are productive sols. We were able to spend most of those sols getting a lot accomplished for the campaigns. The reason they're different colors is the red ones, those are part of multi-sol plans, which somewhat limits our choices. But overall, those are productive sols. The rest of the pie chart, unfortunately, isn't so productive. Just highlighting the purple regions come into play because of restricted sols. Those are cases where, because of the timing of plans, we had restricted sols and we had to drive on one of the earlier sols, which meant those following sols we weren't able to do as much because we didn't know where the rover was in order to do characterization of the area that we were in. And then the green represent challenges with driving, where for some reason we needed to do extra drives and we felt should have been needed to get to some location. It may have been because of poor visibility, we couldn't safely plan routes as far as we wanted to, or it could be that we had a long drive but it faulted out because of too much excess slip was encountered, higher than expected tilts, or visual odometry failed to converge. So some takeaways from this plots is, first of all, you can see there's actually quite a large percentage of sols that aren't as productive as we'd like. So that tells us there is some room to improve here. And the other thing that's interesting is that although it's Pahrump Hills and Marias Pass that had the common campaign objectives, it's actually Artist Drive and Marias Pass that look very similar. They have very similar profiles when you look at it this way. And we concluded, if you look at it, the reason is, and the thing that they actually shared in common was the pattern of restricted sols that they had. They both had relatively few restricted sols compared to the duration of those campaigns, and that just had to do with the luck of the timing and when these things happened. Oh, I guess I meant to mention on the restricted sols, about 40% of our sols are restricted. And so just based on where a campaign lies, where it begins and ends, determines how many restricted sols it's going to be impacted with. And then the green ones are because of terrain challenges. So Pahrump Hills had fairly benign terrain. It was this nice sloping terrain in front of us. We could see it all from the beginning. Whereas Marias Pass and Artist Drive were in very similar terrain with more undulations, more ridges, more occlusions, more areas of sand that we worried about slipping in and getting stuck in, and so that caused a lot more problems. So as I showed on the previous slide, there's room for improving the productivity of sols. The question is, do we have the resources in the vehicle to do so? And so we did a very detailed analysis of looking at energy, time available, thermal conditions, data volume, and looked at how the team was making use of those resources. And again, I'm just going to give you the high-level takeaway from this is, yes, in fact, there are available resources to make use of to do more productive activities. And one takeaway is we noted that the amount of resources the team was using on multi-sol plans was decreasing. So when we create 2-sol plans, we use fewer resources than 1-sol plans, and on 3-sol plans, we use even fewer. And one of the reasons for these campaigns we noted is that the amount of resources we're allocating towards campaign objectives on restricted sols, if we'd driven in the sol before, drops dramatically. And that's, as I mentioned, because we don't know what to target. We don't know if we let the rover drive on the subsequent sols, we wouldn't be able to target where it was because we wouldn't see the data that it collected. One of the ways we then formalized, or not formalized, but came up with a number for how much productivity we were leaving on the table with the vehicle, is we looked at how much energy the vehicle was shunting. And so shunting is what happens when we fully charge the batteries and we still have more energy from the RTG, and we still have more energy from the RTG. We actually just radiate out into the atmosphere. I like to refer to it as our contribution to Mars terraforming. And that's just energy just thrown away. We're not going to get that back, and we didn't make good use of it. So that's in the gray. The blue is time that we had the vehicle on and it was using energy, but not very productively. It was mostly idle. And that can happen, as Eddie mentioned, because we give it this extra margin, and we didn't use that margin a lot of the time. And so the system spends a lot of time with the CPU on burning energy, but not doing much with it. We took very conservative conversion factors to turn those durations of idle time and shunt energy, and concluded that on average for each of these campaigns, we had about 70 hours of extra energy we could have spent productively and still come up with a fully charged battery at the end of the campaign. And to give you an idea of what that means, we typically have, so that's about 3.5 to 4 hours of extra energy per sol that we could have spent. That's about what productive time we spend anyway on the vehicle as it is, so that's almost doubling the amount of time we would be able to have productive activities on the vehicle, which would be, when I show this to operations people, they drool over these numbers and kind of are upset about how much we're not making use of. So some of the challenges that's preventing us from making use of this, oh, there it goes. And again, there's a big list here. I'm not going to go through all these. The major factors were these ground-in-the-loop decision points, and the fact that restricted sols and the limitations of decisional pass timings is limiting our ability to make use of available resources. So we limit what the vehicle can do on after decisional pass. We limit what it does for these campaigns if we drive and then have a restricted sol that follows it. And there's other various things, but those are the two highlights. We also did a characterization of, or a summary of what were these ground-in-the-loop decisions being made. One is simply picking the science targets, figuring out where we're going to point the ChemCam laser spectrometer at, figuring out where we're going to take high-quality multispectral mass cam data of. We need to see the data and tell the rover what we're trying to get accomplished to make those effective decisions. Drive planning really often needs a lot of human intervention. We have the ability on the vehicle to do autonomous navigation, but it doesn't currently understand things like hazards such as slip and sand. And so it's actually a coordinated effort between engineers and science experts to characterize the terrain each day and help the rover find safe paths through the environment. And then I'll skip down to here. Sometimes things don't go as we expect. Observations might not collect the data effectively as we wished. Drives may fault out. And we don't know until the next day or the next 2 days, if depending on the comm relay situation. And so a lot of time gets wasted. And we may have driven away and either have to drive back to redo an observation or just give up on that observation. Okay, so that gets us into where we're looking for to try to address these challenges. And this is a high-level overview of the various changes we're looking at making both to the flight system and ground practices. And to begin with, we'd like to change the interface to the vehicle. Rather than giving it these low-level command sequences that tell it in great detail how to accomplish what we want to get done, we want to give it high-level goals to tell it what we want to accomplish and let it figure out how to do it based on the current state conditions, because we might not know what those state conditions are ahead of time. And in doing so, it can then get a better sense of what actual resources it has available, so it can make more effective use of surplus energy, surplus time that it has available. What can it do with that time productively? Well, we're looking at expanding the role of autonomous science that we have on the vehicles. People may be familiar, we actually have a little bit of autonomous science going on with the Marin and MSL rovers. There's a technology called Aegis, which I'm also involved with, which enables the vehicle to identify, for MSL, it can take post-drive navcam images, find targets that are interest based on scientist input, and then follow up with taking LIBS rasters, ChemCam rasters of them, so it gives the scientists some extra opportunity for data. And it's been very successful on MSL, but we want to grow that capability such that when you go to a new region, we can actually perform some higher level form of characterization of the area to provide even more rich set of data for the scientists to either inform the decision points that they have or collect them data when we don't have ground and loop opportunities, so we don't have to limit the rover so much in what it does. To address the fact that things don't always go as we expect, we're looking at increasing the role of health assessment and health response in rover operations. So we want to make monitoring whenever we perform activities, we want the vehicle to make expectations of how those activities should result, how they should be carried out, and then monitor the progress as it's performing them, identify problems when they're happening, and see on board if we can come up with safe and robust responses to problems that happen so we don't have to wait so long for ground in the loop and waste that time and resources. One of the main areas we're looking at for that purpose is in making multi-sol navigation more robust. So that when drives fault out, the rover can help on its own try to figure out what went wrong, see if it can safely respond to that on board. In some cases, we may not be able to, and so it's important in those cases to realize it does need human intervention, but even so, can then find out what other productive things it can do with its time while it waits for human support. And part of this is also I mentioned that the rovers currently aren't aware of the risks of sand and how those can cause slip. We're making the navigation system more slip aware so it can make those decisions on board. On the ground side, there's a lot of changes that I think need to get made. We really want to change the paradigm of how we operate the vehicles. We want to make it natural for the operators to interact with the vehicle without knowing the state the vehicle will be in when it gets our command products, and that's extremely different from how we interact with the vehicles today. We put together this just to give ourselves some guidance in how we're coming up with these scenarios. This is an overhead view of our Mars yard from Google Earth. Imagine it's well zoomed out, looking like MRO from Mars, and this will make a little bit more sense. But we're looking at two major phases of operations that we're hoping we can provide help with. One is the strategic drives, and we heard from our scientists during our interviews that we have gaps in our understanding of Mars when we're doing these long-range strategic traverse campaigns, because we don't get the opportunity to stop and collect a lot of images that we'd like to get, because it slows things down. And so we're looking at ways that the rover on its own can help collect more rich set of data so that we can fill in those gaps that we otherwise have while we do these long-range traverses without slowing down the campaigns. And then when we get to a region of interest, we want to help them perform, there's a strategy of exploring which is used most commonly by geologists on Earth, but rarely on Mars, where they do a walkabout. When they get to a region, they first survey the area, and on the rover that would mean driving around and using remote sensing, and then make another pass based on what they now understand of the area. They can now better allocate their more time-intensive and resource-intensive resources or activities, such as bringing out the arm and doing close contact study, they can be more informed of those decisions based on that first round of the walkabout. But they don't often do it on Mars because that walkabout has a lot of overhead when you're interacting with the vehicle with these ground and loop interactions. And so we'd like to try to make that a more efficient process where we can do some of that without so much interaction with the science team and the engineering team, but still making use whenever we can of guidance that we can get from them. So then I just have a couple slides just to give you, and this starts to get fuzzier because we're working on this stuff now, and so we haven't fully answered all the questions here. In terms of how we're expanding autonomous science, we're trying to develop what does it mean to characterize an area? And we're working with scientists to try to develop this process. And it's a closed loop process we have in mind where we collect context information, these lower quality wide field of view nav cams, and inside there we have a suite of various algorithms. Some of the stuff similar to what Steve was talking about this morning. For example, texture cam is one of the things in here. To understand what we're seeing, we want to get we want to basically be able to describe what's representative in the scene and what's standing out in the scene, document that, and provide it back to the operators, either to help them make decisions, or if there's not a ground and loop process, just so we can provide that information for their next round of exploration, or just filling in the gaps on a long-range traverse. In terms of making the system more robust as problems happened, this is what we're currently thinking about. This is a multi-phase process where first we detect a fault, and we're not talking about getting rid of current fault detection techniques. Those are still very important. But when a fault is detected, we want to then try to isolate it. And so we're looking at various model-based techniques to try to isolate what subsystems really are at fault here, and then see if we can classify, okay, so we think it's this subsystem, let's classify how it failed. And if we can do that, then the next question is, can we employ the planning process to try to find a response to that, to the way that process has failed, that subsystem has failed. And if we can do so, then maybe we can exonerate some subsystems, we'll exonerate some during the isolation process. Maybe we can clear the problems with this robust response, and then we can let the system either go back using those resources, or in the case that we decide we can't respond to it on board, we can just mark that subsystem as not being used, and then we can update our plan to shed the activities that require that subsystem, but still find things we can do in the meantime that doesn't rely on that subsystem while we wait for help from the ground systems. And this gives a sketch of how we're incorporating this into the mobility system. And what we're trying to do there is try to recreate what the humans and engineers and scientists on the Earth do, where when they characterize the terrain, they form expectations about what the rover should experience in terms of slip and tilt. And then as the rover drives, we set limits on it to say, if you ever exceed these limits, it means we don't understand the terrain. Stop and let's on the Earth reconsider. We're bringing that on board, and such that if its expectations aren't met, we can detect that and then go through a round of isolation and response and classification steps to see if we can figure out what went wrong. Maybe it's because we incorrectly classified the terrain. So can we schedule a time to reassess it, get more imagery, compare it to what the actual data we've been collecting as we've been driving around to see if we can reclassify it. If we encountered a stall, maybe there's some things we can do on board to see if we can extract ourselves from and respond to that stall while still remaining safe. And so that's what we're looking at there. On the ground side of things, as I mentioned, we want to change how we interact with the vehicles such that we're more comfortable interacting with it without knowing exactly what state it's going to be in. And we don't have well, this is just some vague ideas here. We were sort of sketching out what it looks like when we have this ground-in-the-loop interaction without knowing exactly what the vehicle has been up to. We may not know exactly what it did, but we can give you some ideas of what it did based on our expectations, predictions of what resources it had. And then we're also looking at changing our ground tools. They're very much focused right now on the rover, you're going to do this at exactly this time, exactly this way, and very detailed. And we want to loosen that up so that we can give the vehicle more high-level directives, such as acquire me multispectral mass cam imagery of a particular rock formation as you're driving around, and be able to provide that guidance in the tool and let the rover figure out how to accomplish that, when to accomplish that, based on when it sees those events and the resource levels that it has. I'm almost done here. So we're also looking at how this interacts with lower level flight systems. One thing we're looking at is bringing a ground tool that's not currently part of flight systems into the flight system. It's a target database. And this is how the operators on the Earth talk to each other in terms of what's looking interesting on Mars on a given day. They put these targets in, and engineers and scientists communicate with the target database. We actually think that can be useful on board to let our various subsystems, and that picture didn't come through. There's various subsystems here that can, like the planning system, science system, and navigation system, that need to talk about targets, and they can talk to each other through this target database. We can also tell the Earth about the targets that we found, and let the Earth tell us about targets that it thinks the rover should know about through that database if we can synchronize them. More traditional capabilities on flight systems, such as data products and EHA, we have such valuable information that the rover collects, but we package it up and send it down to Earth with giving very difficult access on board to that information. And so we're looking at ways to improve access to that so we can respond, investigate science opportunities in the science data and make sure we can assess the vehicle state and resource levels with the telemetry data. And so finally, this is the report I've been talking about. There's many, many more details about the case study in that report. Go to our AI website, go to Publications 2016, and you'll find it. And the main takeaways is, yes, we've found there are a lot of challenges to productivity, but there's lots of opportunities to improve on that if we can overcome these challenges. And I'll thank my great team I have working with me, and I also want to give a huge thanks to the MSL mission, which was incredibly supportive of us in doing this case study, and we couldn't have done it without them. So thank you.
Yes, hold on. We have a ton of people online.
Okay.
You guys know that this is on YouTube? Have we done that already? You can just search for Flight Software Workshop.
What's the maximum power usage during any operational phase?
Like instantaneous power, or like energy across a day?
Well, across an hour or some a shorter period of time. But what's the?
Well, I'll tell you our
sort of
conversion
maximum
rate.
average?
So we took 200 watt hours. We said is very conservatively about an hour of either driving or remote sensing. It's actually more like 150, 180 watt hours.
Yeah.
So that's, I think, probably.
For an hour. And what's the battery capacity?
I don't remember. I'm not. We might have that in the case study report. I think it's online. I'm sorry, I don't remember.
Okay, thanks.
Other questions?
Yes.
Hold on.
So I'm curious, have you done any analysis comparing the current cadence to the first 3 months of the MER mission, where the operators were tracking the souls, and what was the utilization rate like at that point, or do you have a rough idea?
So I didn't do that for MER. I myself was part of the MSL team during those first 30 days, so I could maybe just anecdotally comment on that. And it was much lower then, because we were actually learning how to operate the vehicle during those first 30 days as well, or actually 90 days when we're on Mars time. So we actually decided not to use one of those earlier days to study, because it's kind of unfair, I think, to poke at productivity during those days, because the team really is still trying to learn how to operate the vehicle. Now, you could counter argument being, well, maybe we need to do more operational tests and drills ahead of time to better learn these things, and that would be true. It's just a matter of budgeting and time to be able to do that kind of stuff.
Questions? Nope. Very good. Thank you.
Thank you.